Welcome! Today, we will be exploring LeetCode problem number 1964, titled Find the longest valid obstacle course at each position. This problem challenges us to think critically about dynamic programming and efficient data structures to solve a unique sequence problem. Let's dive in and see how we can approach this step by step. In this problem, we are tasked with finding the longest valid obstacle course at each position in an array. The input is an integer array called obstacles, where each element represents the height of an obstacle. For every position I in the array, we need to determine the length of the longest sequence of obstacles starting from some earlier index j and ending at I that satisfies one key condition: the obstacle heights in the sequence must be non-decreasing. This means that each obstacle in the sequence must be less than or equal to the height of the next one. Our goal is to return an array called answer, where each element at index I represents the length of the longest valid obstacle course ending at that position. The problem specifies the input format as a single integer array and the output format as another integer array of the same length containing the results for each position. Let's look at the first example to understand the problem better. If the input obstacles array is 1, 2, 3, 2, 1, 5, 1, the output is 1, 2, 3, 3, 2, 4, 2. Here's how the output is determined for each index. For I equals 0, the only course is 1, so the length is 1. For I equals 1, the sequence 1, 2 is the longest valid course, and its length is 2. For I equals 2, we extend the course to 1, 2, 3, making the length 3. At I equals 3, the course can be 1, 2, 2, which is still valid since it's non-decreasing, so the length is 3. For I equals 4, the course resets to 1, 1, giving a length of 2. At I equals 5, the sequence 1, 2, 3, 5 is the longest course, and its length is 4. Finally, for I equals 6, the valid course is 1, 1, again, with a length of 2. Now, let's examine the second example. If the input array is 2, 2, 1, the output is 1, 2, 1. For I equals 0, the course is simply 2, so the length is 1. For I equals 1, the sequence 2, 2 is valid because the heights are non-decreasing, giving a length of 2. For I equals 2, the course resets to 1 since no previous elements can extend the sequence, resulting in a length of 1. Let's also consider the third example where the input is 3, 1, 5, 6, 4, 2. The output in this case is 1, 1, 2, 3, 2, 2. For I equals 0, the course is 3 with a length of 1. At I equals 1, the course is 1, also with a length of 1. At I equals 2, the sequence 3, 5 is valid, so the length is 2. For I equals 3, the course extends to 3, 5, 6, giving a length of 3. At I equals 4, the sequence resets to 3, 4 with a length of 2. Finally, for I equals 5, the course is 2, resulting in a length of 2. Let's break down the explanation for the third example in more detail. For I equals 0, the sequence starts with just the first obstacle, 3, so the length is 1. For I equals 1, since 1 is less than 3, the sequence is limited to 1, and the length remains 1. At I equals 2, we can form the sequence 3, 5, because 5 is greater than or equal to 3, giving a length of 2. For I equals 3, the sequence extends further to 3, 5, 6, as 6 is greater than or equal to 5, resulting in a length of 3. At I equals 4, the sequence decreases to 3, 4, since 4 is less than 6, so the length is 2. Lastly, for I equals 5, the obstacle height 2 results in the sequence 2, with a length of 2. This demonstrates how the algorithm tracks the longest valid course dynamically, ensuring the heights remain non-decreasing. The constraints of the problem indicate that the input array can have up to 10^5 elements, and each height can be as large as 10^7. This means the solution must be efficient, ideally with a time complexity close to n log n, to handle the large input size. Let's also consider some edge cases. If the array has only one element, such as obstacles equals 5, the result is 1, since there's only one obstacle in the course. If all elements are the same, like 3, 3, 3, 3, the result is 1, 2, 3, 4, as each obstacle extends the previous course. For strictly decreasing heights, such as 5, 4, 3, 2, the result is 1, 1, 1, 1, as no sequence can extend past a single element. These examples highlight the importance of designing an efficient algorithm to handle these diverse scenarios. To solve the problem of finding the longest valid obstacle course at each position, we first consider the brute force approach. The intuition here is straightforward. For each index I in the array, we look at all previous indices j where j is less than or equal to I. For each of these indices, we check if the obstacle at position j is less than or equal to the obstacle at position I. If it is, we calculate the length of the subsequence ending at I and keep track of the maximum length. This can be implemented using a nested loop, where the outer loop iterates through the obstacles array, and the inner loop checks all previous indices to determine the maximum valid subsequence length for each position. However, this approach has a significant drawback. Its time complexity is O(n squared), making it computationally expensive for large arrays. For example, if the array has up to 10 to the power of 5 elements, this approach becomes infeasible. While simple to understand, the brute force method highlights the need for a more efficient solution for larger inputs. To overcome the inefficiency of brute force, we move to an optimized approach that leverages binary search. The key intuition here is that we can reduce the problem to finding the position of each obstacle within a non-decreasing sequence of potential valid subsequence lengths. This is achieved by dynamically maintaining a DP list, where each DP, I, represents the smallest possible ending value of a subsequence of length I plus 1. For each obstacle, we use the bisect_right function to perform a binary search on the DP list. This tells us the longest subsequence in which the current obstacle can fit. After determining this position, we update the DP list with the obstacle value at the correct index. This approach has a time complexity of O(n log n), thanks to the efficiency of binary search, and it is much faster than the brute force method. While this strategy is highly efficient, it does require a solid understanding of binary search and careful handling of edge cases during implementation. Another optimized approach involves using a Fenwick tree, also known as a binary index tree, to solve the problem. The key idea here is to use the tree to efficiently maintain and query the frequency of obstacle heights. First, we normalize the obstacle heights to fit within the tree's range. Then, for each obstacle, we query the Fenwick tree to find the maximum length of a subsequence that can end at the current obstacle height. After finding this length, we update the tree with the new subsequence length at the respective position. Like the binary search method, this approach has a time complexity of O(n log n), as both updates and queries in the Fenwick tree are logarithmic. However, it does introduce additional space overhead and is less intuitive to implement compared to the binary search method. While this method matches the performance of the binary search approach, its complexity makes it a less practical choice for most scenarios. The problem can be closely compared to finding the longest non-decreasing subsequence, LNDS, at each position, and binary search provides a highly efficient way to solve it. By dynamically building and updating the DP list, we simulate the subsequence construction process in an optimal manner. The key realization here is that binary search allows us to quickly locate the correct position for updating the DP list, which significantly reduces the computational overhead. When we weigh the trade-offs, the brute force approach is impractical due to its O(n squared) complexity, while the Fenwick tree approach, though efficient, adds extra space requirements and complexity. The binary search method emerges as the best choice, offering an ideal balance of performance, simplicity, and space efficiency, making it the most practical and scalable solution for this problem. To tackle the problem, find the longest valid obstacle course at each position, we need to determine, for each index in the given array of obstacles, the length of the longest subsequence ending at that position such that all elements in the subsequence are less than or equal to the current obstacle. The key to solving this efficiently lies in combining binary search with dynamic programming, using a greedy approach. First, let's break down the problem. The input is an array of integers called obstacles with constraints that it can have up to 100,000 elements and values as large as 10 million. The output is another array, where each position represents the length of the longest valid subsequence up to that point in the input. Our goal is to solve this in O(n log n) time complexity, which is necessary given the constraints. To achieve this, we rely on two key observations. First, the length of the longest subsequence ending at any position depends on the values in the subsequence leading up to it, and second, binary search allows us to efficiently determine where the current obstacle fits in the context of maintaining subsequences. This insight enables us to dynamically build the solution as we iterate through the array. Now, let's dive into the algorithm. We start by initializing two structures. First, a list called least that will store the smallest possible ending values of subsequences of various lengths. This list remains sorted and non-decreasing, enabling efficient binary search. Second, an array called result, of the same size as the input, which will store the output for each position. As we iterate through the obstacles array, for each element, we perform a binary search on the least array to determine its appropriate position. Specifically, this position tells us the length of the longest valid subsequence that ends at the current index. If the position corresponds to the end of the least array, we append the obstacle to least, signifying the creation of a longer subsequence. If not, we replace the element at that position in least with the current obstacle, ensuring that we maintain the smallest possible ending value for subsequences of that length. After determining the position, we update the result array at the current index with the position value increment by 1, since positions in least are zero-based. Once the iteration is complete, the result array contains the desired output for all indices. An important aspect of this approach is how the data structures least and result work together. The least list dynamically grows and shrinks based on the input, making it space efficient. It stores the smallest possible ending values for subsequences, allowing us to find the optimal placement for each obstacle in logarithmic time. The result array, on the other hand, stores the computed lengths for each position and is updated in constant time during the iteration. In terms of complexity, the binary search operation performed for each obstacle takes O log n time, and since we process every element in the input array, the overall time complexity is O n log n. The space complexity is O n as well, since the least array and result array together require space proportional to the size of the input. Several edge cases are worth considering. For instance, if the array has a single element, the result is simply 1. For a strictly increasing sequence, the result is a sequence of consecutive integers starting from 1. For a strictly decreasing sequence, the result is all ones. If all elements are equal, the result is also a sequence of consecutive integers, as each new element extends the previous subsequence. To solidify our understanding, let's go through an example. Consider the input array obstacles as 1, 2, 3, 2, 1, 5, 1. We initialize least as an empty list and result as an empty array. Processing the first element, 1, we append it to least since it starts a new subsequence. The least becomes 1, and result is updated to 1. For the next element, 2, we append it to least as well, extending the subsequence. Now, least is 1, 2, and result is 1, 2. The process continues similarly for 3, which is also appended, resulting in least being 1, 2, 3, and result 1, 2, 3. When we encounter the second 2, we replace the 3 in least with 2 to maintain the smallest possible ending value for a subsequence of length 3. The least remains 1, 2, 3, and result becomes 1, 2, 3, 2. For the next element, 1, it replaces the first element in least, resulting in 1, 2, 3, while result is updated to 1, 2, 3, 2, 1. Next, 5 is appended to least, making it 1, 2, 3, 5, and result updates to 1, 2, 3, 2, 1, 4. Finally, the last one replaces the first element in least, leaving it unchanged as 1, 2, 3, 5, and updating result to 1, 2, 3, 2, 1, 4, 1. The final output is 1, 2, 3, 2, 1, 4, 1. This implementation solves LeetCode problem number 1964, find the longest valid obstacle course at each position, using a combination of dynamic programming, DP, and binary search for efficiency. Here's the step-by-step explanation. 1. Imports. The code uses the bisect_write function from the bisect module to perform binary search efficiently. 2. Class setup. The longest obstacle course at each position method is implemented within the solution class. It takes a list obstacles as input. 3. Initialization. N. Length of the input list obstacles. Result, an empty list to store the length of the longest valid obstacle course at each position. dp, an empty list that will track the smallest ending values of increasing subsequences. 4. Main loop. The code iterates through each obstacle in the obstacles list. For each obstacle, it finds its position in dp using bisect_right. This gives the index where the obstacle can either extend an existing subsequence or replace an element to maintain the smallest possible values in dp. 5. Updating dp. If the position POS is equal to the length of dp, the obstacle is greater than all elements in dp, so it is appended. Otherwise, the obstacle replaces the element at position POS to keep the subsequence values minimal while maintaining order. 6. Result update. The length of the valid obstacle course ending at the current index is POS plus 1, because indices are zero-based. This value is appended to the result list. 7. Return result. After processing all obstacles, the result list is returned, containing the desired lengths for each position. ### complexity. Time complexity. The algorithm runs in O(n*log n) because for each obstacle, the binary search, bisect_right, operates in O log n. Space complexity, O(n), for the dp list. This implementation is efficient and handles edge cases such as non-increasing or non-decreasing sequences seamlessly. It guarantees correctness by maintaining the smallest possible values in dp, enabling binary search to work effectively at every step. To solve the problem of finding the longest valid obstacle course at each position, we start by defining a method longest obstacle course at each position. The input is an array of integers representing the obstacles. First, we initialize an array result to store the lengths for each position and a list dp to keep track of the smallest possible ending values of increasing subsequences. As we iterate through the obstacles, for each obstacle, we determine its position in the dp list using a helper method called binary search right. This position tells us where the current obstacle can either extend or replace a value in the subsequence. If the position equals the size of the dp list, it means the obstacle can extend the subsequence, so we append it. Otherwise, we replace the element at the calculated position in dp. Finally, we record the length of the subsequence ending at the current position, which is calculated as POS plus 1, and store it in the result array. The helper method binary search right is used to find the appropriate position in the dp list for the current obstacle. This method performs a binary search to locate the first position where the value in dp exceeds the target. The search is conducted within the range from left to right, and at each step, we calculate the middle index mid. If the value at mid is less than or equal to the target, we move the left pointer to mid plus 1. Otherwise, we adjust the right pointer to mid. Once the loop exits, left will point to the correct position. This efficient binary search ensures that we find the position in logarithmic time, which is crucial for maintaining the overall efficiency of the solution. By combining this method with the main logic, we can determine the longest obstacle course at each position in optimal time. In this example, we start with the input array 1, 2, 3, 2, 1. First, we initialize three variables, n as the length of the input array, which is 5, result as an empty list to store the lengths of the valid obstacle courses at each position, and dp as an empty list to track the smallest ending values of increasing subsequences. Now, for the first obstacle, which is 1, we use the bisect_right function on dp to find the position where 1 can be placed. The result is POS equals 0. Since POS equals the length of dp, we append 1 to dp, making it 1. We then append POS plus 1, which is 1, to result, resulting in 1. For the second obstacle, 2, using bisect_right on dp gives POS equals 1, allowing 2 to extend the sequence. Again, as POS equals the length of dp, we append 2 to dp, updating it to 1, 2. Then, we append POS plus 1, which is 2, to result, making it 1, 2 so far. Next, we process the obstacle 3. Using bisect_right, dp 3 results in POS equals 2, meaning 3 can extend the sequence further. As POS equals the length of dp, we append 3 to dp, which now becomes 1, 2, 3. We then append POS plus 1, or 3, to result, making it 1, 2, 3. For the next obstacle, 2, we use bisect_right, dp, 2, which gives POS equals 2, indicating that 2 can replace the value at index 2 in dp. This replacement updates dp to 1, 2, 2. We append POS plus 1, which is 3, to result, resulting in 1, 2, 3, 3. Finally, for the obstacle 1, using bisect_right, dp, 1, gives POS equals 1, so 1 replaces the value at index 1 in dp. This updates dp to 1, 1, 2. We append POS plus 1, or 2, to result, giving us the final output for this example, 1, 2, 3, 3, 2. For the next example, the input array is 4, 1, 5, 3, 6, 2. We initialize n as 6, result as an empty list, and dp as an empty list. Processing the first obstacle 4, we use bisect_right, dp, 4, to find POS equals 0, so 4 is appended to dp, making it 4. We append POS plus 1, or 1, to result, resulting in 1. For the second obstacle, 1, bisect_right, dp, 1, gives POS equals 0, so 1 replaces the value at index 0 in dp. This updates dp to 1, and we append POS plus 1, which is 1, to result, resulting in 1, 1. For the third obstacle, 5, bisect_right, dp, 5, gives POS equals 1, so 5 is appended to dp, updating it to 1, 5. We append POS plus 1, or 2, to result, making it 1, 1, 2 so far. Now, for the obstacle 3, using bisect_right, dp, 3, results in POS equals 1, so 3 replaces the value at index 1 in dp. This updates dp to 1, 3. Appending POS plus 1, which is 2, to result gives 1, 1, 2, 2. Next, for the obstacle 6, bisect_right, dp, 6, gives POS equals 2, so 6 is appended to dp, updating it to 1, 3, 6. We append POS plus 1, or 3, to result, resulting in 1, 1, 2, 2, 3. Finally, for the obstacle 2, bisect_right, dp, 2, gives POS equals 1, so 2 replaces the value at index 1 in dp. This updates dp to 1, 2, 6, and appending POS plus 1, which is 2, to result gives the final output for this example, 1, 1, 2, 2, 3, 2. For the third example, the input array is 3, 3, 3, 3. We initialize n as 4, result as an empty list, and dp as an empty list. For the first obstacle, 3, bisect_right, dp, 3, gives POS equals 0, so 3 is appended to dp, making it 3. We append POS plus 1, or 1, to result, resulting in 1. For the next obstacle, 3, bisect_right, dp, 3, gives POS equals 1, so 3 is appended to dp, updating it to 3, 3. We append POS plus 1, or 2, to result, making it 1, 2. Then, for the third obstacle 3, bisect_right, dp, 3, results in POS equals 2, so 3 is appended to dp. This updates dp to 3, 3, 3, and appending POS plus 1, which is 3, to result gives 1, 2, 3, so far. Finally, for the last obstacle 3, bisect_right, dp, 3, gives POS equals 3, so 3 is appended to dp, updating it to 3, 3, 3, 3. We append POS plus 1, or 4, to result, resulting in the final output for this example, 1, 2, 3, 4. To analyze the time complexity of this solution, we start by examining the outer loop. The algorithm iterates through the entire obstacles array, which means it runs n times, where n is the length of the array. For each obstacle, the algorithm performs a binary search using the bisect_right function. This function locates the position where the current obstacle should be inserted or replaced in the dp array. Since the binary search operation depends on the length of the dp array, it has a time complexity of O log k, where k is the size of the dp array at that moment. In the worst-case scenario, k can grow up to n, such as when the input array is non-decreasing. Combining these two factors, the outer loop executes n times, and each execution involves a binary search that takes O log k. Thus, the overall time complexity of the solution becomes O n asterisk log n. Now, let's consider the space complexity of the solution. The primary contributor to space usage is the dp array, which stores the smallest ending values of valid subsequences. In the worst case, if all obstacles are strictly increasing, the DP array will grow to size n, requiring O(n) space. Additionally, the result array stores the length of the longest valid obstacle course at each position, and since it has the same size as the input obstacles array, it also requires O(n) space. Beyond these, the algorithm uses only a few auxiliary variables, such as n, pos, and obstacle, which require constant space, or O(1). When we combine these contributions, the total space complexity of the solution is O(n) for the DP array plus O(n) for the result array, resulting in an overall space complexity of O(n). When comparing this optimized approach to a naive solution, the efficiency improvements become clear. A brute force method would involve iterating over all previous elements for each obstacle to determine the longest valid subsequence ending at that position. This would result in O(n) operations for each obstacle, leading to an overall time complexity of O(n squared). On the other hand, the optimized solution leverages a binary search via bisect_right to maintain the DP array efficiently. This reduces the time complexity from O(n squared to O(n* log n, while maintaining the same space complexity of O(n). This significant reduction in time complexity makes the optimized approach far more suitable for large input sizes. Finally, let's analyze the algorithm across best, average, and worst-case scenarios. In the best case, where all elements in the array are equal, the algorithm still processes each element and performs a binary search for each, resulting in a time complexity of O(n* log n. For the average case, the input array typically has varying patterns, but the binary search ensures that the overall complexity does not exceed O(n* log n. Even in the worst case, such as when all elements are strictly increasing, the DP array grows to its maximum size of n. However, due to the efficiency of binary search, the time complexity still remains O(n* log n. To mathematically prove this big O bound, note that binary search operates in O log k, where k is the size of the DP array, and inserting or replacing elements in the DP array is O(1). Since the outer loop runs n times, the total work performed is O(n* log k. With k being at most n, this simplifies to O(n* log n, confirming the algorithm's efficiency. One common mistake in this problem is confusing non-decreasing with strictly increasing. Remember, the sequence allows equal values, so duplicates are perfectly valid. If you mistakenly assume the sequence must be strictly increasing, your solution will fail. To fix this, ensure that comparisons use less than or equal to instead of less than. Another frequent pitfall is relying on a brute force approach. Iterating through all previous indices for every position results in an inefficient O(n squared solution, which becomes impractical as the input size grows. Instead, you should use binary search combined with a data structure like a Fenwick tree, segment tree, or sorted array to reduce complexity to O(n log n. Lastly, errors in binary search implementation are also common. This often happens when trying to find the correct position to extend or replace an element in the subsequence. To avoid this, carefully track how the binary search bounds are updated and thoroughly test edge cases to catch any mistakes. Another issue arises when edge cases are not handled properly. For instance, what happens if all obstacles are the same, or the sequence is strictly decreasing, or there's only one obstacle? These cases can break your solution if not accounted for, so it's important to test thoroughly against these scenarios. Additionally, mismanaging indices in Fenwick trees or segment trees is a common source of errors. Off-by-one mistakes are particularly prevalent when working with these data structures. To address this, take the time to document how indices map to the tree structure and verify whether you're using zero-based or one-based indexing. This small but critical step can save you a lot of debugging time. This problem is essentially a variation of the longest increasing subsequence, LIS, with the added twist of allowing duplicates and requiring a non-decreasing order. As such, it's a great way to test your understanding of dynamic programming in binary search. Key techniques include leveraging binary search alongside a Fenwick tree or segment tree for efficient updates and queries. Interviewers are often looking for your ability to optimize brute force solutions and apply binary search to problems beyond simple sorting tasks. They also want to see your comfort with advanced data structures like Fenwick trees. Common follow-up questions might include how you would modify the solution to handle dynamic obstacle additions or adapt the algorithm for even larger input constraints, such as n greater than 10 to the power of 5. There are several related problems that build on similar concepts. For example, the longest increasing subsequence problem, which is LeetCode number 300, uses binary search and dynamic programming techniques that are directly applicable here. Another is the Russian doll envelopes problem, LeetCode number 354, which extends the LAS concept into 2 dimensions. The longest bitonic subsequence problem, LeetCode number 376, introduces the challenge of combining increasing and decreasing sequences. Finally, the maximum sum increasing subsequence, LeetCode number 1035, adds a layer of complexity by requiring optimization of the sum alongside the sequence itself. Alongside these problems, alternative approaches to solving this one include using a Fenwick tree. This approach stores the longest valid obstacle course length at each value, offering an n log n complexity. While efficient, it does require careful handling of indices. Another approach is to use dynamic programming combined with binary search. This involves maintaining a list where each element represents the smallest obstacle that can end a sequence of a given length. This method is also n log n, and is generally simpler to implement than a Fenwick tree, though it's less flexible when it comes to dynamic updates. Alternatively, you could use a segment tree for range queries and updates on the sequence. While this approach offers more flexibility, it's more memory intensive than a Fenwick tree. Each of these methods has its trade-offs, so the choice of approach often depends on the specific requirements and constraints of the problem you're solving. To wrap up, this problem demonstrates the power of combining binary search with dynamic programming for efficiency. It's a great example of solving sequence-based challenges with optimal algorithms. Thank you for following along, and we hope this walkthrough adds value to your coding journey. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!